This tutorial is going to show you how to take a quadratic expression that is in standard form and rewrite it in vertex form using a technique called completing the square. Now, if we were asked to express this function, which is in standard form, in vertex form, well, if we knew the vertex, the actual coordinates of the vertex, we could just quickly write the vertex form equation and be done with it. And so you might want to think that, okay, well, what if we did this? What if we took a look at the graph of this function? And you said, okay, well, there's the graph. Can I find the vertex? And I think you can see that right here, we've got the vertex of this function. And I think we can clearly see that it appears to land at -3. So there's the line -3, and 5, 6, and there's -7. So it looks as though the vertex here is at -3 and -7. Okay, well, in order to write the equation in vertex form, we would need to write f at x equals some sort of a value, which is the stepping pattern, and then the coordinates of the vertex would actually be included inside and outside a perfect square. Because this is -3, we would have x plus 3 inside, and the -7 on the end would be -7. And the question becomes, well, what the heck is this stepping pattern here? Well, if I look at the vertex, I can see that we start at this point, and if I go over 1 on the normal parabola, the parent function y equals x squared, I would expect to go up 1, and that would be an a value of 1. In this parabola, however, we see that it goes up to there. So it goes up 2. So we go over 1, up 2, and that means that the a value would be 2. So there is the equation in vertex form. And you'll notice that the a value matches the a value up top there. Okay, well, that's one way to do it. You could actually, if you had a picture of the graph, you could actually take a look, try and pull off the vertex, try and pull off the stepping pattern, and just write vertex form right away. Unfortunately, it doesn't always work that nicely, because the vertex may not land on an integer grid line. It may not be easy to tell from the graph what the stepping pattern is. So to find out the exact coordinates of the vertex and to make sure that your answer is dead on, we're going to actually use the algebraic method of completing the square. So there's a number of steps that we use to go through and complete the square. And these are the steps we're going to go through. And we'll just take them one at a time, and it'll be nice and easy. And when we're all done, if all has gone well, we should have the exact same formula that we just wrote on that little graph. So first step, step 1, factor out the a value. And we can see that the a value is 2. Okay, so I'm going to factor out that 2 out of this equation here. And the important thing is that I'm only going to factor it out of the first 2 terms. That is, the terms that contain an x variable. Okay, I'm not going to touch the 11 at the end. It's going to stay outside the brackets. I'm just going to factor the first 2 terms. So what's left inside the brackets? Well, if I take 2x squared and I divide it by 2, I'm left with x squared. And if I take 12x and divide it by 2, I'm left with positive 6x. Okay, so that's step 1 done. Factor out the a value. Perfect. Step 2, take half of the middle coefficient, in this case it's a 6, and square it. All right, so I'll take 6. I'll just do my rough work here. And I'm going to take half of it. So I'm going to multiply that by a half. And I know that that is going to equal half of 6 is 3. Okay, now I take that 3 and I square it. And that gives me 9. This value of 9, so this little process of taking half of the middle coefficient and then squaring it, gives me a value that turns these two terms into a perfect square when I add it on the end. So if I rewrite this line one more time, and in this case, I include the start, which we had as x squared plus 6x. Then I'm going to add 9 and immediately subtract 9. And by adding and subtracting the same value, I've basically added 0 to the equation. So I haven't changed the equation at all. So I haven't broken any rules. The equation is still valid. Okay, I essentially added 0 to the equation. But here's what that accomplished. If I now focus on these first three terms, well, those are a perfect square. And I can rewrite a perfect square in its compact. Think of it as like putting it in a suitcase or reducing it down. And I can reduce it down to just x plus, and remember this value over here, this 3, the half of the middle term, that is the value that goes on there, squared. And if you're not convinced that this x plus 3 squared does in fact generate x squared plus 6x plus 9, go ahead and expand this out as some rough work. Do FOIL on it, and you will see that in fact this is the short form representation of this perfect square. So once we have this short form representation of the perfect square, well, what do we do next? Well, here's what we need to do. This is still inside these brackets here. So these blue brackets, they didn't go away. They're still sitting there. And I'm just going to make them look like square brackets so you can tell the difference. The -9, it wasn't part of the perfect square. It's still sitting there. The 2 out front, still there. And the 11 on the end, still there as well. So how do we, it's looking, a little closer to vertex form, how do we go ahead and complete it? Well, all we need to do is we're going to complete step 4, which is distribute the a value. So here's the a value at the front, the 2. And I'm going to multiply it into these blue square brackets, and I'm going to multiply it by the first term and the second term, and that's going to give me the following. 2 times this first term is 2, and then x plus 3 squared, and 2 times -9 is -18. This is looking a lot like vertex form now. I can't forget about the plus 11 on the end, and that leads us into step 5. And step 5 just says collect all of the terms. And the terms that we can collect and combine together are these two constant values at the end. So the last line I would write is 2 times x plus 3 squared, and -18 plus 11 leaves me with -7. And where is the vertex now? Well, the vertex in this equation is at, well, the plus 3 in here, that means the vertex is at -3, and then the y value of the vertex is sitting at the end there, -7. So that seems to match what we saw before. And let's just go back and take a look at that graph. Here is the graph of the original function, and you can see that sure enough, here is the -3 and -7, the coordinates of the vertex, and the other points that you'll see on here are the roots. You've got one root there and one root there. And how do you find the roots? Well, normally to find the roots we would factor, but this equation of 2x squared plus 12x plus 11, it doesn't factor nicely at all. You have to use the quadratic formula to come up with these two roots. So what I would like you to do is go ahead and on your own, there's the answers, so you can check your answers, take and find the roots of this quadratic function that's given to you in standard form, and you should find that you get these two values right here. Okay, so to summarize, when we are taking a look at standard form and we're interested in the vertex, using the technique of completing the square can quickly turn standard form into vertex form, and once we've got an equation in vertex form, we can read off the vertex with no problem whatsoever.